Yeah. Okay. Thank you, Jen, for the introduction, and it's a great pleasure to give this talk here. And this is actually a very recent work. So I'm going to describe a new mechanism on superconductivity from repulsive interactions. And as Jen said, this was actually motivated by recent experiments on Moire materials. But as we explore this more and more, it's now going different directions. So I won't be able to say too much today about Moire materials, but you will see that this is a motivation. Okay, so yeah. Let's continue.
Okay.
Yeah, could you?
Yeah. Can you see the screen?
Okay, yeah. So yeah, perfect. Yeah. Maybe let me turn off my video to save some bandwidth. Yeah.
By the way,
so this work is actually done with.
By the way, would you like we ask questions during the talk?
Oh yeah, please.
In the end. Okay.
Oh, please, feel free to interrupt anytime. Yeah.
Sure.
Yes. Yeah. So this work is done with two brilliant collaborators. So it started. I started working on superconductivity in Moire materials with Kevin Slago, who is a postdoc at Caltech, and more recently, this work inspired some recent works I did with my student Valentin Krapel at MIT. So today, I probably won't have time to talk about all of these three pieces of work. So I'll focus more on the recent works with Val. Yes. Okay. So as we all know, the Bardeen-Cooper-Schrieffer theory successfully explains superconductivity in conventional metals, and here the attractive interaction between electrons come from the electron-phonon interaction, and this attraction is limited to low energy within the Bi frequency. On the other hand, there's a much larger Coulomb repulsion, direct Coulomb repulsion between electrons. And so really, if we look at the interaction as a function of energy, everywhere at all energies, the interaction is repulsive. It's just that within the Bi frequency, it's less repulsive. And what made it still possible to get a pairing is this crucial retardation effect. So basically, because the Fermi energy is much greater than the Debye energy, there's a large renormalization effect. The Coulomb interaction becomes strongly reduced at low energy. So pictorially, you can think of the following. When two electrons repel, they move away from each other. And as they move apart, the Coulomb repulsion, which is inversely proportional to the distance, then become weaker. Okay. So this retardation condition is essential. The large separation of energy scales between the Fermi energy and the Bi frequency make it possible for superconductivity to occur in conventional metals. But then, as we move on to the Moire materials, Jay, could you, next slide? So as we see in the last several years, that superconductivity has found in systems with very narrow bands, and here in magic angle graphene, the bandwidth of the flat band is probably only on the order of 10 millielectron volt, and yet find a superconductivity over a wide range of filling of these flat bands. Next slide, please. So so in these flat band systems, the bandwidth is so small, and the dominant interaction is the Coulomb repulsion. So this sort of raises the question: is it possible that in flat bands, in narrow band systems, could electron repulsion drive superconductivity directly without involving phonons, or maybe phonons only play a minor role? So this is, of course, a very interesting question that has been studied for a long time in the context of many materials, strongly correlated materials, also including high TC, heavy fermion systems, and etc. Next slide. So there is one approach which leads to pairing and the superconductivity from repulsive interactions, and this is known as a Kohn-Lechtinger mechanism. it works in the weak coupling limit. So when the repulsion is small, then one can show by a controlled analysis that attractive interaction emerges. And intuitively, this can be understood as an electron would polarize the entire Fermi liquid, and that induces a polarized Fermi in the presence of the Fermi surface. There's induces a Friedel oscillation, and Friedel oscillation leads to attractive regions at a finite distance. And this mechanism then gives rise to finite element pairing. And this is an asymptotically exact method. It's controlled in the weakly interacting limit. Of course, the problem is that in that scenario, the TC is exponentially small. So not only is exponentially small in the interaction, but really the pairing interaction itself is a second order effect. So it's proportional to the bare repulsion squared divided by the bandwidth squared. So this is a very small, it will only give rise to a very small TC compared to the Fermi energy. So that's why it's a control method only in the weak coupling limit. That is, generally speaking, not so physically relevant in real materials. Next slide, please. So now, as I already mentioned, the superconductivity has been found in many correlated systems, and in particular, these superconducting states seems to be very robust, and the ratio of the transition temperature and the Fermi temperature is substantially higher than conventional metals. It can reaches between 1% to 10% of the Fermi temperature. And this is also the case in magic angle graphene, as well as the more recently discovered magic angle trilayer graphene. And in particular, in the latter case, this very recent work from MIT, my colleague Pablo's group, shows that the TC over TF can actually reach about 10% at optimum conditions. So this is quite remarkable. So the question then is there a good theory of strong coupling superconductivity that from repulsive interaction, and strong coupling means large TC-TF ratio. Next slide. So this is of course a very challenging problem, and I think I can think of at least three aspects. So generally speaking, it's very hard to find an analytic control method to handling systems with strong interactions. And in numerical simulations, these systems generally have a sign problem. So it's exponentially hard to deal with large system size. And also on physical grounds, in systems with strong repulsion, superconductivity often competes with other states. And for example, in the recent work from the Simon's collaboration, it was found that for the pure Haber model on the square lattice, in the strongly interacting regime, where U is 6 to 8 times the hopping T, the ground state is non-superconducting, and it's non-superconducting for an interesting reason, that superconductivity is suppressed by a competing state, and that is a stripe state. So this illustrates the excuse me, yeah, illustrates the challenge of handling strongly repulsive systems and searching for superconductivity in such systems. Next slide. So so this is sort of a brief overview of what I'm going to describe today. So I'm going to show you some new ideas where in systems with strong interaction with narrow bands, we propose a 3-particle mechanism for superconductivity. So I will describe how the 3rd particle comes in the pairing. And we're going to introduce a method. It's based on expansion, not in the interaction, but in kinetic energy terms. Okay, so we're going to deal with lattice systems, and we're going to do an expansion in the hopping T between sides. So this is a non-perturbative method in interaction strength. And the outcome is that we can actually handle strong coupling superconductivity in the presence of a strong electron repulsion. Next slide. So yeah, so this work with Val-Kreppel, this controlled method for dealing with superconductivity in narrowband systems. Yes, next. So so let me start with a concrete example to illustrate this general idea. And so let's consider this toy model of fermions on honeycomb lattice. The two sublattice A and B with a different on-site energy. So the sublattice potential difference we call delta, and there's nearest neighbor hopping T, and then there's nearest neighbor repulsion V. So later we're going to generalize this model to the spin-full case and to this case with longer range interactions. Next slide. So this is yeah. Hello.
Hello. Yes.
Okay. Yeah.
Can you hear us? Yeah. Okay.
Okay. Yeah. Okay. So yeah. Okay. Good. Are we still connected?
Yes.
Yeah,
yes.
we can hear you now.
Oh, is this good now?
We can hear you now.
Okay, great. Yeah. Can we move on to the next slide? Yeah, sorry. Yeah. Okay, so in this very simple model, let's first consider the case of a fitting of 1 electron per unit cell. And in this case, the ground state is insulator. This insulator is adiabatic connected to the atomic limit. If the hopping T is turned off, then it's clear that at this fitting of 1 electron per unit cell, all electrons want to be in A sublattice because the B side has a higher energy delta. It's also adiabatic connected to the non-interacting limit when the V, nearest neighbor repulsion, is turned to 0. In that case, we know that in band theory, this is just a band insulator of ionic character. There's a conduction and valence bands, and the band width is only order of T squared over delta, and there's a gap delta between them. So the band width is much smaller than the band gap. Okay, so and when you include the interactions, one can still ask, what is the band width of one added electron, one dope electron, and in that case, the band width is further reduced. And so this system basically looks a completely boring insulator. Okay, it's a band insulator. It's a non-topological, purely ionic, as boring as you can imagine. So the question now is, what happens if you dope this boring band insulator? Next slide. So so I'm going to show that remarkably, upon doping, superconducting state emerges with F-wave symmetry. So to remind you, this is a spinless systems. So the pairing has to be unconventional. And moreover, this superconducting state has a strong coupling character. In particular, at the small doping, we have an analytical result for the TC that is shown here. TC is proportional to the square root of the doping density delta. And it depends exponentially on this coupling constant G0. This G0 expression for G0 is shown here. It depends on the bare repulsion in V and depends on the bare gap delta. So the expression for G0 is non-perturbative in interaction strength. And this formula for TC holds at small doping and is accurate up to TC around 0.1 Fermi energy, TF. Okay, so this, so as you increase the interaction strength, then the coupling constant G0 increases and the TC will increases with it. And this formula that I'm showing here is reliable is quantitatively accurate even when Tc reaches 10% of the Fermi temperature. So that's a very strong coupling superconducting state. Moreover, the ratio of the superconducting gap and Tc is 4.79. It's much higher than the BCS value, which is 1.75. Okay. So let me now describe how these results are obtained. Next slide. By the way, please feel free to interrupt and ask questions. Okay, so the method we're going to use is this strong coupling expansion in the kinetic term. So in this model, we have only nearest neighbor hoppings. So if you want to describe to the first order of T, you always create holes on the A site, and this is a high energy excitation. So instead, in order to describe the low energy physics of doped electrons that live on the B sites, we have to start with the second order process. Okay, so we're going to now derive the second order through this second order effect. We're going to derive an effective Hamiltonian, and so in the figure shown here, I illustrate all kinds of second order processes, and for example, what's shown on the left is that if you just think about the ground state, due to the virtual tunneling of an A site electron to an adjacent B site and then come back, it renormalizes the ground state energy, even in the absence of any doped electrons. And then the second figure shows that the second panel shows the second the second region shows that in the presence of one doped electron, then some of the virtual processes is still present, but some are suppressed because now some of the virtual transitions is blocked by this presence of the red dots, right? Of electron red dots. So therefore, this effectively modifies the basically the So let me continue. So yeah, basically the third panel shows basically a hopping of the electron on the B side to an adjacent B side is through a second order process, and then the next panel shows that the density interaction between two adjacent B electrons is induced by a virtual process involving an adjacent A electron, and finally the last panel shows that when we'll talk about the third one in a minute. Yeah, so let me move on to the next slide first.
Yeah, I have one quick question. Yeah. Is these two different color these two represent basically the same quasi-particle, the same color?
The red dots just mean the electron on the B sides, and the blue dots mean the electron.
I mean you have two figures for the green dotted line. Is this two basically representing the same quasi-particles?
It represents the intermediate states, which I'll talk about in the next slide. Yes.
Okay.
I also have a question, which is, so there's no spin so far, right?
Yes, no spin so far.
So does that mean so just electrons are not allowed to hop onto occupied sites? Is that the rule?
Yeah, that's correct.
There can be no double occupancy because there's no spin.
There's no double occupancy. Yes, absolutely. Yes. But later we'll introduce spin. Yeah. Okay. So yeah, so the intermediate states in this second order process, it involves composite excitations that involve holes on the A sites. So these can be dipoles, polarons, and trimers, and they all have different energies. That's shown here. Okay, next slide. Okay, so the final result is this. So before that, can we go back to the? Yeah. Okay, this is fine. This is fine. Okay. So sorry again. Yeah. So can we go back to the Schrieffer transformation?
This one.
Yeah. So this is the Hamiltonian we derived. It includes the hopping. So this Hamiltonian basically governs the physics of doped electrons on B sites. So it includes single particle hopping, TF, the nearest neighbor repulsion, VF, but as well as the correlated hopping. So the hopping from side I to K depends on the occupation of another adjacent side J. Okay, so that turned out to be the crucial term. And there's also three-body interaction. So so here I've shown the exact expressions. This results are exact to second order in T squared. It's valid at any doping and for any interaction V. Okay? And I want to emphasize that this effective interaction is instantaneous because we only integrate out high energy degrees of freedom. So as far as the the dynamics of the doped electron is concerned, the interaction is instantaneous on the scale of its bandwidths. And also I want to emphasize that longer range interactions in the original model can be included straightforwardly. So when the longer range interactions are present, we basically renormalize these energy denominators in the expression for these effective parameters. So essentially, longer range interaction renormalize the energy of the polarons, trimers, etc. So it can be handled very conveniently.
Sorry, Liang.
Yeah.
Question. So presumably F creates a F wave pair. That's the operator in the Hamiltonian.
F is just, you mean the subscript?
F,
no, F creates an electron.
F dagger, right, creates a F
Electron.
wave pair. Is that correct?
No, F creates just an electron on the B side. F is a Fermion operator.
F is a Fermion operator on the B side. Okay.
B sides. Yeah. So thank you. Sorry for.
Okay. So you're probably going to get to it. The reason there's no P wave is there's some symmetry argument.
So we didn't find any attractive interaction in the P wave channel.
Mm-hmm.
And so the simplest way to understand this is just think about like one unit cell with one A wave side and 3 adjacent B side. And if you do that like a two electron calculation in that 4 sites cluster, you will find that there's only F wave.
Uh-huh.
Yeah. So another way of saying this is, I think, yeah. Okay. Yeah, next slide.
Thanks.
Sorry, I also have a quick question. So is that doping mainly changing like the hopping process related to some like adjacent sets, or like does it related to one whole singularity or other things?
So this Hamiltonian is exact for any doping, but we need to analyze then the ground state of this Hamiltonian for different densities for different dopings. So the ground state may change as a function of doping. Yes. Okay, good. Next slide. So here I want to then illustrate the emergence of correlated hopping, and this is where the 3-particle mechanism comes in. So so again, I'm trying to illustrate the case of a doped electron at side I hops to adjacent B side K. So the hopping this has to occur through a second order process where the adjacent A side hops first, and then the vacancy is filled in by the electron from side I. But then this hopping process, depending on whether another adjacent side J is occupied or not, it involves intermediate state of different energy, right? Because of the repulsion V is present. Okay, so in the left case, the intermediate state has energy which is delta plus V. This is when side J is empty. When side J is occupied, the intermediate state has energy which is just delta. So because of this difference in the energy of the intermediate state, it leads to different hopping amplitudes. So that's why both the single particle hopping and correlated hopping appears. So if the bare repulsion V is 0, then the effective hopping from I to K is just given by T squared over delta. And there's no correlated hopping. This is a non-interacting problem. But as soon as V is present, then the hopping from side I to K, the amplitude depends on whether side J is occupied or not. And that just means that there's a correlated hopping. Okay. So, so as we see that this is where what I meant by 3 particles, there's when 2 doped electrons on side I and side J, and then the virtual process involves an electron that's sort of away from the Fermi energy, right? In the occupied bands, that is the site on side A, right? So the 3 particles are involved to give you this correlated hopping of 2 doped electrons. Okay, next slide.
So one quick question. So if the V equals 0, the lambda will be 0.
Yes. Yes.
Right. How to understand that?
Oh, because it's a non-interacting system. In the
So
non-interacting
lambda
system, lambda is correlated hopping. So if you go to the previous slide, so lambda is a term that's an interaction term. Right?
I see. This one.
Yeah, that's right.
Okay. Thank you.
Yeah. Next slide. Okay. And yeah, indeed, you know, so we can actually look at the small v limit. In a small v limit, then the natural way to think about it is to first think about the formation of bands due to the hopping T, and then we project the interaction into this narrow band. And in that case, because of the one-year function in the conduction band is mostly on B side, but it has a small mixture with the A side. And the Baire interaction V is between nearest neighbor A, B sides. And therefore, once you project the Baire interaction into this conduction band, you find a much smaller effective repulsion between doped electrons, which is proportional to T squared over delta squared. But you also find correlated hopping. So correlated hopping emerges very naturally, okay? It already appears if you direct project the interaction into the narrow band. But interestingly, if you do this direct projection, then the correlated hopping magnitude is 1/2 of the nearest neighbor repulsion. Okay, and we will see that this actually produces no pairing. Okay, so if you do direct projection into the narrow bands, although we do get the same type of is such that there's no attractive pairing interaction. However, next slide. If we go beyond this small v limit, so what this plot shows is that interaction strength of the Baire interaction v over delta. So the x-axis on the log scale. So the dashed line is what you would obtain if you just do the direct projection into the conduction band without taking into account of virtual interband processes. While the solid line is what we obtain from this exact. Okay, so the solid line is what we obtain exactly from this Schrieffer-Wolff transformation. That is exact in the narrowband limit. And you see that
Sorry, sorry, I will lost you after you said the solid line is the exact in the Schrieffer transformation.
Yeah. Okay. So right. So so the exact transformation shows that the effective interaction strength deviates strongly, right, from the direct projection, and in particular, we see that the correlated hopping lambda actually is the ratio of the correlated hopping and the density repulsion exceeds 1/2. Okay, exceeds 1/2. And also I want to emphasize that this was in particular when the V is less than delta, the induced interactions between doped charges are much smaller than the band widths. So even though the original model is strongly interacting, when V can be already on the order of the band gap, much smaller, much bigger than the band width, the low energy physics, right, of doped electrons has only a weak and intermediate interaction strength. Okay, weak and intermediate. So we've transformed the strongly interacting problem to a system of intermediate correlation for the doped electrons. So next slide. Okay, so so what's really remarkable is that pairing occurs right away. If you just even consider just 2 doped electrons, we find there's already a 2-particle bond state. So this is obtained by solving the exact lattice model of the effective Hamiltonian, and we see that the Cooper pair has F-wave symmetry, and we plot the binding energy as a function of the pair interaction strength V over delta, and we see that as the V over delta increases, the system goes to even the doped electrons become stronger and stronger correlated, right? So the Cooper pair size shrinks to essentially Y lattice constant at a very large V over delta. And however, we're going to mostly focus on V over delta around 1. So that in our regime, the Cooper pair size is still large. So this is where we have an analytically controlled theory. Next slide. So this again shows that the pairing occurs in such a simple model with purely repulsive interactions, and this sounds very unusual, but we also check this. So my student Val did an enormous amount of diagonalization study. So here I'm showing the binding energy from a full calculation of the entire honeycomb model with 30 sites, and again you can see the binding energy and pairing correlation develops as you increase V. Yes, next slide.
May I ask whether this crossed line is extracted to infinity system size, or what it means?
Extrapolation, yeah,
Okay.
exactly. Okay. Yes, it's extrapolation for different system size. Yes.
Thanks.
Okay, so then after finding the pairing for two particles, then actually we can extend this calculation to finite density. And here, let me just start by using the mean field theory. Okay, so although the original model has only pure repulsion, the effective Hamiltonian from the Schrieffer transformation already have attractive pairing interaction in the F-wave channel. So then we can then do mean field study, and we find the pairings interaction strength is related to these interaction terms in the effective Hamiltonian, 2 lambda minus VF, and then also 3-body repulsion we treated in a mean field manner. So one thing I want to emphasize again is that if we directly do a projection of the original pair interaction without taking into account of interband processes, then the pairing interaction in the F-wave channel is exactly 0. So this again says interband renormalization is crucial for pairing. So so here we show also the TC as a function of the interaction strength V, and you see that TC will reach all the way up to about 10% of Fermi energy, and as we increase the interaction strength, and also there's an early question about doping dependence. When the doping is small, less than 1/4, the Fermi surface around the K and K prime point. Okay, and in that case, the F-wave pairing leads to a fully gapped state. As the doping increases above 1/4, then the Fermi surface become a singly connected pocket around the gamma point, and then the F-wave order parameter has nodes along the gamma m direction, so it will lead to then a nodal F-wave state. And one can imagine that also right at the 1/4 fitting, or in the vicinity of 1/4 fitting, then this Van Hoff singularity and may lead to competing states between the density waves and superconductivity and etc. So next slide. So of course, the mean field theory is only reliable when the effective interaction is somewhat small. However, there's another regime where the theory can be extended to stronger interaction strength, and this is at low density limit. So in the low density limit, we can then go to the continuum description. The doped electrons that live at the bottom of the conduction band, that's around K and K prime point, and expanding the Hamiltonian around this K and K prime, basically it gives rise to a 2-valley electron gas. And because it's a spinless system, the only interaction that is relevant in the RG sense is a contact interaction between the 2 valleys, the dense interaction between the 2 valleys. And I want to emphasize that we have actually exact derivation. We start from this effective model on the lattice, and we can transform it into the continuum theory. So we know the parameters in the continuum theory. So the coupling constant G is proportional to VF minus 2 lambda, and it is negative. So we have attraction. So then this theory basically is exactly the BCS problem of attractive Fermi gas in 2 dimensions. And here the valley plays a role of spin. Right? Even though there's no physical spin, there's 2 valley degree of freedom. And also this inter-valley spin singlet pairing precisely corresponds to F-wave pairing on the lattice, because under reflection symmetry, you exchange the 2 valleys, and in the spin singlet pairing, when you interchange spin up and spin down, you pick up minus sign. So this precisely corresponds to F-wave pairing in the lattice model. Next slide. So also just to show that this derivation is really a good approximation. So we compared the binding energy from this continuum theory, the BCS problem, with our lattice calculations. So here the binding energy depends on the UV cutoff and depends on the coupling constant G0. And as I said, we already have full expression for G0. And for the UV cutoff, it's fixed by the exact lattice calculation when the Baire interaction V is sent to infinity. So in that case, we know the binding energy exactly. So this fixes the UV cutoff. And then we can actually compare the results. So next slide. So here, I'm again showing the solid line is the result from the exact lattice calculation, and the dotted line is from the continuum theory without parameters, without any adjustable parameters. Or you can say with one parameter that is fixed by the behavior at V equal infinity. And you see that perfect agreement. So this again tells us that this derivation is from the lattice to the continuum theory is justified. Okay, next slide. So once we have transformed the problem at low density to this BCS problem, we can say a lot based on the known results. And in fact, I see Shiwei Zhang is here. I think some of he did some of the most important Monte Carlo simulations on this BCS problem in 2 dimensions. So in the low density regime, but not too low density, we are still in the BCS regime. And then this is expression for KBTC, and it's proportional to the square root of the Fermi energy and the binding energy, the 2-particle binding energy. And then if we express in terms of the microscopic parameters, it's shown here. Okay, and this formula is accurate from the Monte Carlo result. It is known that this formula is quantitatively accurate even when the TC reaches 10% of TF. So what I've done is basically show that starting from a repulsive model on the lattice, we can actually get strong coupling superconductivity. Okay, so next slide. And also, I want to emphasize that even though the doped electrons are in the BCS limit, the ratio of the gap in TC is 4.79, much larger than the BCS value. And the reason is the following. In the BCS theory applied to conventional metals, the pairing interaction only is limited within the Debye frequency range, and the Debye frequency is much smaller than Fermi energy. While here, in our case, as well as in actual cold atom systems, the pairing interaction is non-retarded. It spreads over the entire bands of the entire narrow bands, and the bandwidth is larger than the Fermi energy. So in that case, the TC receives contribution from all states in the band, not just from a narrow window around the Fermi energy. So because of that, delta over TC is much larger. Next slide.
May I ask one question here? So in this figure is a dot obtained by numerical simulation of the TC over TF, and the solid line is from the continuous series. So that's why they match
exactly. Yes. So solid dots, the dots are obtained from lattice calculation, the lattice mean field calculation, while the solid line is according to this continuum theory prediction.
I
The
see.
extraction
So that's because the continuum theory only develops for near K and K prime region. So that's why there's no continuum theory for the red, for
That's
the
right.
blue dot.
Exactly. Exactly.
Uh-huh.
Yes.
And this line is the bound recently.
This
hit.
one is a bound. Yes. Yes. So yes, again, there are real experts on this BCS problem in the audience. But for parabolic dispersion, and there's a bound on the TC over TF. This is in the BCS-BC crossover regime, this bound is saturated. Yeah, and here I'm only showing you the result according to this BCS formula. Yeah.
I see. So why there are two numerical dots above the bound?
So as I said, these are all from mean field calculation. Right? The solid dots as well as the solid line is obtained from the mean field calculation, and the mean field calculation will fail as you go to the BEC side. As you increase the interaction strength, the quasi-particles also become strongly interacting with each other, and then this approximation will break down. So that's why I said this formula is only valid up to TC around 0.1 TF.
Okay. So what is this dashed line again?
Dashed line is based on the BEC-BSS extrapolation. Yes, so you would expect then in a real system, it should follow more the dashed line. Yeah.
Thanks.
Yeah. Okay. Okay. So so we also did meaning again everything, all this calculation is done by Bao. Yeah. So the numerical exactization study for the case of up to 6 particles, 6 doped particles, and you can see the ground state energy in panel A as a function of the flux. You see this H over 2E flux dependence. This is evidence of pairing. And the panel B shows the superconducting stiffness as a function of V over delta. And again, the finite stiffness implies superconductivity. And finally, in panel C, we show the pairing gap defined as the energy difference by adding and subtracting 1 electrons. We see the binding and the pair gap delta as a function of the interaction strength V. And again, you see that it shows superconductivity. Yeah. Okay. And in fact, at small v, the coherence sense is large, so finite size effect is strong. But you see that as v over delta approaches 1, it agrees. The exactization study agrees with the analytical results, which is a dashed line. Right. Now, at even larger v over delta, then even the quasi-particles become strongly interacting with each other, and we are approaching something else, the BEC regime, and also strongly coupling regime. Next slide. Yeah, also, as we increase the particle density, we find an interesting case that in the large range of interaction strength, we see that the superconducting stiffness is already present, but the pairing gap is either 0 or very small. So this we interpret as the nodal superconductivity. When you're doping above the Van Hove singularity, the F-wave order parameter has nodes. Yes. Next slide. So I stayed much away from this large V limit when the band interaction in V is much bigger than the band gap. Then something else happens. Here, the color represents the superfluid conducting stiffness. And you see that at higher doping, at large V, the stiffness dropped to 0. So, so we believe, and also in the exactization, we see that there's many degenerate ground state. So we interpret that as phase separation. So even with this model, at a very large interaction strength V, then the low energy theory also becomes strongly interacting. So there's, I think, a lot of interesting stuff there, as a function of doping, which we are still exploring. But the analytical results, it is valid at the low doping and at intermediate V over delta. And that region, we already obtained strong coupling superconductivity with TC over TF up to about 10%. Next slide. Okay, so here I also want to say that if we include the longer range interactions, so if the longer range interaction V2 or V3, etc., are small compared to the band gap, then the leading effect is to they can be directly added to the effective model, the effective Hamiltonian for doped electrons. And what we found is that the superconducting state is actually remarkably robust against the longer range interactions. So this comes from the exactization study. Okay, next slide. Okay, so so far I've been when did I start this talk? 11:30. Yeah. Okay, so let me quickly let me quickly go through the more recent work. So far I've described basically spinless systems as a toy model. It might be useful for cold atom systems. In particular, in cold atom systems, the interaction is indeed short ranged, and there's intensive search for basically high angular momentum pairing in cold atom systems. And in free space, that is hard by the formation of molecules and losses. But maybe what our model says that maybe if you have an optical lattice for spin polarized fermions with short range repulsion, superconductivity can occur reliably in that system with unconventional F-wave symmetry. Okay, so now let me discuss the case of more interest to solid state systems. These are spin 1/2 systems. And one classic example of superconductivity is in strongly correlated systems is of course the high TC cuprates. And actually in cuprates, you also have two types of bands, right? There's the bands from the copper d orbitals and the bands from the oxygen p orbitals. And the system at half filling is actually a mod or charge transfer insulator. You have a local moments on the copper sides, and doped electrons actually go to oxygen, right? So this is what's called a charge transfer insulator. So it has a lot of similar flavor as the toy model I've described, right? But it's a spin-full version of that. Now, of course, doping the mod insulator is very hard precisely because you have a lot of local moments. So even at the filling of n=1, we cannot neglect the physics of local moments. So in the spinless model, at the filling of n=1, I have a complete boring insulator without any spin degree of freedom. That's what made the problem simple, right? So, so next slide. So I'm not going to discuss the mod problem here, but on the other hand, there's also a lot of interesting experiments showing superconductivity arises by doping a band insulator. Okay, so so for example, here in this phase diagram, here you can see a lot of materials like strontium titanate. It's a classic example. It has a large gap band insulator, but doping, very small amount of doping, give rise to superconductivity with a very large, TC over TF ratio. And it's remarkable that, for Fermi energy as small as 1 milli-electron volt, superconductivity still appears. Okay, so, and there are many other materials, germanium telluride, tin telluride, lead telluride. These are all semiconductors, and upon doping, they give rise to superconductivity. And another material is copper doped bismuth selenide, something I thought a lot about. Okay, so then question is, can this mechanism that I described describe superconductivity from those? Hello, yeah, we're still connected.
Yes.
Sorry. Let me move to a different room. I think now the yeah. Okay. Okay, so yeah, where did we end just now? Okay, doping a band insulator. Okay, yeah, can people hear me?
Yes.
Okay, yeah, maybe maybe next slide. Yeah. Okay, so very quickly, let me now talk about the second version of our model with spin. And of course, with spin, one can add also the local Hubbard U on both A sides and B sides, and otherwise the model is the same, right? So next slide. So I won't go through all the derivations again, just to show the same kind of a Schrieffer-Wolff transformation. We can eliminate the high energy processes and to derive an effective Hamiltonian for the doped electrons. And again, the form of the effective Hamiltonian is very similar. There's there's now an on-site energy U for just because of the local repulsion. There's a correlated hopping just like before. There's also another correlated hopping between just two sites, which turned out to be not important at all. So so what we found is just solving the two-particle problem. You see that F-wave bound state in a large parameter range. So here, panel B shows the binding energy as a function of the nearest neighbor repulsion V in the Bayer model, and for various different interaction on-site Hubbard U.
I have a question here.
Yes.
You're not taking U, the on-site Hubbard, to be large, right?
So
because
it can be actually very large. So in fact, I'll show you next slide the phase diagram. So
then I get a spin model.
Because okay, one thing I should emphasize that here we find the bound state only in the spin triplet channel.
Okay.
So the triplet naturally avoids the on-site U. Yeah, that's an excellent question. Yeah, next slide. So this is the phase diagram. You see that this white dashed line separates the superconducting and non-superconducting region, or regions with and without attractive pairing interaction. So you see that if the on-site U is large, then you actually need a critical, you need the repulsion V to above a critical value to enter the superconducting region, right? So therefore, it is essential that this theory is non-perturbative in interaction strength. Okay. Also, we checked that even at the level of two doped electrons, the bound state formation is stable it's perturbatively stable against long-range coulomb interactions. So if we include further long-range interaction, bound state is still there for finite, over a finite range of interaction strengths. Next slide. So once again, at low density, we get a two-valley Fermi liquid. But now, because we have a spin degrees of freedom, the interaction is more interesting. There's a repulsion within each valley. There's a density repulsion between the two valleys, G1, and there's a spin exchange interaction between the two valleys, G2. This kind of interband processes actually produce sufficiently strong ferromagnetic exchange interaction, and then that leads to the triplet pairing. Okay, so the G2 is turned out to be greater than 4 times G1, and that's why we can get a triplet pairing. Next slide. So so this is the prediction then that is very striking. You dope a band insulator, and immediately spin triplet valley singlet superconducting state will be obtained, and this will be a state with a full gap. And the TC again goes as square root of doping. Okay, so next slide. So yeah, so let me quickly summarize the theoretical results so far. We've shown that in narrowband systems, the motion of nearby carriers on the lattice will be correlated. Okay, so the effective hopping will depend on whether a neighboring particle is present or not. And we developed a strong coupling expansion based on the kinetic terms. And this gives a controlled way to handle superconductivity from strong repulsive interaction. And the correlated tunneling of 3 particles induce pairing within the narrow band. And TC can reach as large as 10% of TF at low density when the theory is still controlled. And this happens when the Bayer interaction and single particle band gap are comparable. And the unconventional pairing symmetry, such as F-wave and spin triplet, is obtained. Next slide. So far, everything I've described is based on simple models. So I like to start. I always like to start. This is what I learned from my PhD. I always like to start with simple models, and then the question is that, of course, having understood fully simple models, does it say anything useful about real systems? Next slide. So the question then is, Okay, the road to reality. Next slide. So let me just describe the one material that caught our attention and which we think our theory might be useful, say something useful. So this is a monolayer tungsten ditelluride. This is a material that we predicted several years ago that it should be a 2D topological insulator from band inversion. And you see that the conduction band is mostly the d orbital of tungsten. The valence band is mostly the p bands of tellurium, but just near gamma point, there's band inversion. And this band inversion then should create a topology and one-dimensional edge states. And later, indeed, evidence for the helical conductance through helical edge modes was observed in transport experiments. Next slide. Now, what's really remarkable is that in 2018, two different groups from MIT and from University of Washington, Seattle, they both found superconductivity in electron-doped tungsten ditelluride. And these are basically resistance as a function of temperature for different dopings controlled by the electrostatic gate voltage. And at least it looks like the direct transition from insulating behavior to superconducting behavior. So there's no evidence of an intervening metallic state. It really looks like doping turns an insulator into a superconductor. And also what's interesting that if you go to the previous slide, in the conduction band of tungsten ditelluride, you actually see that there are two electron valleys, right? So although this system does not have hexagonal lattice symmetry, one feature that it has is that there are two valleys in the conduction band. So electron doping would create a two-valley electron gas. At low density, you expect the system to be a two-valley electron gas, just like what our toy model does. Okay, next slide. Yeah, next one. So there's also some tentative reports. I think this is still something that needs to be digested. But there's some, at least some experiments saying that there may be some extonic effects in tungsten ditelluride. That fact that the observed gap, both in transport and in STM tunneling, is much larger than what DFT theory predicts. So these were attributed to some kind of extonic effects. So then natural question is, so we have an insulator and with strong extonic effects, meaning the interband renormalization is important. So then can our theory basically describe this WTE2? So then our prediction is that it should be spin triplet. Next slide. So so one thing we compared is our theory with experimental data from Pablo's group, TC as a function of the gate voltage, which is proportional to doping. And we do see that at low density, the TC rises as a square root of density, right? So this is again unusual because in the BCS framework, we would expect that in 2D systems, density state is constant, independent of energy. And the BCS theory says TC is controlled basically by density state. So then you want to expect that TC is nearly independent density. While if you look at in all these theories that I've described, as well as in cold atom systems, the pairing interaction is not limited to the vicinity of the Fermi level. And for that reason, the TC would have a strong density dependence, and it should go at square root density. This is a very robust result, and it matches nicely with experiments. And then our theory would also predict that the single particle gap should not close, and the delta over TC should be significantly larger than the BCS value. So these are all can be verified by future STM experiments. Next slide. Also, regarding the triplet nature, so the experiments actually already observed back in 2018 a very large violation of Pauli limit. So when you apply in-plane critical magnetic field, the superconducting state survives even when the critical field is much larger than the Pauli limit. Okay, so of course, there are other scenarios where this large Pauli violation can be explained, but this is certainly consistent with the triplet pairing. Next slide. Now, this is what caught my attention. That if you look at the previous slide, this is previous slide is data from Pablo's group. you see that at a small magnetic field, the TC actually seems to increase under a magnetic field before it decreases again, right? There are essentially only 3 data points, so maybe one should not make too much a big deal out of it. And certainly the authors didn't even comment on it. But then next slide, yeah. But it's interesting that the same year, there's another experiment from Michigan group on epitaxially grown thin films of tungsten diterite, about 5 nanometers thick. And these authors, they actually realized that there's a magnetic field enhancement of TC, and that was a focus on their work. And they met tremendous trouble with referees. This is my understanding from talking to Lu. For example, if you look at resistance as a function of in-plane magnetic field, you see that the superconducting transition occurs at higher temperature under in-plane magnetic field. So the right panel is a plot of the TC dependence on magnetic field, and you see clearly, with now there are many, many more data points, and you see that TC actually increases first when you apply a small magnetic field, in-plane field. Next slide. So we then actually thought about how this can be understood within the framework of triplet pairing. So in our picture of the triplet pairing, it has a D vector because the triplet pairing has a spin quantization axis, and the spin quantization axis can free to rotate if you don't have spin orbit coupling. And then when you apply in-plane magnetic field, the Zeeman energy of the triplet pairs would actually enter. So in the free energy, there's a term which is B dot D cross conjugate of D. So this term essentially describes the effect of Zeeman energy of the triplet pair. So once we include that term, we can then obtain a very simple result, how TC depends on magnetic field. There should be a linear term and then a quadratic term. The quadratic term just comes from the ordinary pair breaking of optical effect, while the linear term comes from this Zeeman term. And then we actually can fit the experimental data with theory. You can see a very nice agreement. So again, this tells us, makes us believe that superconducting state in tungsten diterite is actually a spin triplet. Next slide. So okay, I think I'll just leave it here. So I've already summarized the theoretical work, and finally, I just want to mention that in addition to tungsten diterite, we believe that this triplet superconductivity from this interband renormalization can also possibly be relevant to niobium diselenide. There's a recent experiment from Cornell showing that as a function of the in-plane magnetic field, there's a hysteresis in the superconducting gap. So again, the triplet order parameter allows the D vector to reorient. So this may possibly explain also this niobium diselenide. Okay, thank you. Yeah. Sorry that there's a lot of technology problems. Yep.
So I have a question about the last part first, which is, does the topology of the tungsten diselenide matter? So I know there's other cases. Yeah. That's
an excellent question. Definitely. So right. So our model is certainly non-topological, while tungsten diterite is topological. So so this is something we're still thinking. How do you handle topology? Now, one thing I want to say that our model actually includes both bands, right? Yeah. So we start with both A and B sublattice. So I think in principle it has an ingredient to capture topology. But indeed, this is something that we are still thinking about. Yes, yes, it's non-trivial. Yeah. So one thing at a time. So one thing at a time. Yeah. So when you combine topology, superconductivity, and correlation, it's just too hard. So. Yeah, fair enough. The other thing I was wondering is, so you were saying in the beginning, I think this was about the Hubbard model, but basically there's a competition between superconductivity and other phases. You mentioned the stripe phase. Right. So should I understand your work as saying that there is a superconducting ground state regardless of other phases, or is it that the point is that there's a mechanism for superconductivity, but a person would need to look more detailed to figure out the competition with other phases? Yeah, this is an excellent question. So this is an excellent question. So so basically what we showed is that usually people start with single band Hubbard model, right? In the single band Hubbard model, then there's a everything, there's only a limited amount of parameters. It's basically Hubbard U, right? And the Hubbard U then leads to competing states at a high density, not at a density around half filling, right? So the case I'm looking at is like what I'm looking at is like in the multiband system, so in the multiband system, even at the first stage, which is like in chemistry called downfolding, right? If you want to derive effective Hamiltonian only for the electrons in the conduction band by integrating out the valence band, right? So what I'm showing is that that downfolding process itself is already interesting. It already generates attractive pairing interaction for the doped electrons. It's not just Hubbard U anymore, but you will obtain things like coordinate hopping, right? And this coordinate hopping already provides an attractive pairing interaction. So that's why even for just two doped electrons already form a bound state. Now, then the next step is that what happens at finite doping density? At low density, then the theory is controlled. There's no competing state because at the low density limit, we just have a simple electron gas, two-value electron gas. And if there's an attractive interaction at the level of two particles, then it's guaranteed to be superconducting at a small density. But you're absolutely right that if you go to higher density, when, for example, approaching the Van-Hoff singularity, etc., then there may be other competing states. Yes, high density, there something else may happen. But what's interesting is that even at high density, the effective interaction already have attractive pairing instability. So it could be that superconducting state is much more robust compared to other states. So, generically, if you have a superconducting instability, I think the system would, I think it's much more likely the system will just become a superconductor. Right? The problem with Hubbard model is that at the level of a mean field, there's no superconducting instability. Right? So then that's why this competition has to come in. Yes. But this is a great question. Yes.
So sorry, can I ask you a question?
Sure.
Yeah, I have a question. In the first part, you talked about the virtual process of the pairing. So is it possible to have a higher order virtual process instead of the third? Okay.
Yeah, so certainly that's something we are thinking of as well, that you can go beyond the second order, right? Go beyond t squared. And I mean, analytical calculation become very hard. So it's you can imagine, as you can imagine.
Yeah.
So we are thinking of some kind of just starting to think about some numerical approaches. I think there are maybe a lot more experts. So I think something that
and also, what would be the effect of if I start with a lattice that already has let's say second order hopping in the system?
Yes, that's a good question. I don't think it will change very much. I don't think it will change very much. Yes.
I see. So having the second order hopping doesn't affect, doesn't favor more virtual processes.
Oh, it will. I think it will. Actually, I think it will. Yeah. So in that sense, it could actually help. Yeah. It could help. Yes. Excellent point. Yes. And also, I want to say that, in the sort of a broader picture, right? So this, this interband renormalization, you can think of some kind of extone mediated pairing. So I'm basically creating virtual extons, and the extone mediated pairing has a long history. Goes back to work in the 60s and 70s, and but then the problem is that if you rely on the Coulomb interaction, right, for extone physics, the system is a strongly interacting system, so it's hard to do. It has been hard to do this problem analytically. So this strong coupling expansion we have in the kinetic energy provides an analytical methods to handle this problem. And we also obtained unconventional pairing. And sometimes not surprising, the repulsive system, S-wave pairing is strongly disfavored. So in the old days when people talk about extone, people are always having in mind just S-wave pairing. They think that just replacing the phonons by extons. But what we show is that when you do the everything exactly, in the narrow band limit, then you actually get a much richer physics. You can get analytical control and you get unconventional pairing.
Yeah, thank you.
Hi, Liang. Nice to meet you.
Hey, good. Yeah, never met before, I guess.
Beautiful. Yeah, I think when you gave a quantum cafe, I was out of town a year ago or something, a couple of years ago. But beautiful work and beautiful talk, beautiful interrupted talk. So I wanted to follow up on Jen's comment. I had the same sort of thought, whether these whether superconductivity could be kind of intercepted or preempted by other orders.
Yeah.
It's interesting that so in the 3-band model, which you actually mentioned, the copper oxygen plane, sort of the Emery model, we had computed the whole binding energy. So you consistently find binding. So there's
really?
binding energy.
I see.
Apparently, no superconducting order. Of course, this is quite old work. We're not absolutely sure about the lack of superconducting order, but it just looks remarkably similar to the Hubbard model. So to the newer work in the Hubbard model, where we're more sure. Embarrassingly, in the Hubbard model, we haven't really systematically computed the binding energy, whole binding energy. So there's a kind of a logical gap that it's possible that you know, if you see binding, the rest of your logic goes through. But is there a possibility? I mean, I guess in principle there is, but how likely is it if you have, for example, antiferromagnetism and antiferromagnetism that this gets preempted?
Yeah, that's an excellent question. So in my case, you know, either when I talk about spinless version or when I talk about spin-full version, right, I stayed away from the mod case, which is 1 electron per unit cell, right? That's mod insulator, precisely for this reason that if you think about the mod insulator, right, then there's a spin degree of freedom that has to be accounted for, and in the case of the cuprates, the ground state is actually an antiferromagnet. So when you dope electrons into it, either 1 electron or 2 electron, there's still this vast sea of local moments that form an antiferromagnet. And we know that doping, you know, extremely tiny amount of the electron will not destroy the antiferromagnet right away. Right? So these are ingredients that are avoided by either going to the spinless version or by dealing with doping a band insulator. Right? So in those cases, in the case of the spinless case or basically doping a band insulator, then I think the logic follows through that if I have binding energy of 2 electrons, I will get superconductivity right away, because the low energy theory is just electron gas with attractive interaction. Yeah, it's really like the BCS-BEC problem. Very much like the BC-BCS. You know, BC-BCS problem that you have a bonding energy of 2 electrons, two fermions in vacuum, right? In vacuum. Here it's not quite like that. Here I have 2 added electrons in the band insulator, but band insulator doesn't have any active degrees of freedom, right? So in that sense, it's almost like a vacuum, right? But the difference is that when I have a band insulator as a background, even though repulsive interaction, right? Even though the bare interaction in the model is repulsive, I can actually create a virtual polarization that leads to attractive interaction between doped electrons. Yeah.
Could there be phase separation in between?
At a finite density and at a large interaction V, there will be phase separation. So I have one slide that we talked a little bit about that. Yeah, at large density, at large doping and a large interaction V, there will be phase separation, but not at small doping and not for intermediate V over delta. Yeah. Because in the low density limit, right, you know, we literally can think that the system is so dilute, right? And if I have a 2-particle attraction, the electrons will first form just molecules, right? And in fact, there's even a BEC regime at very low density. I didn't talk too much about it because it's probably not relevant to solid state systems. But yeah, but I totally agree with you that in the case of if you have an antiferromagnetic background, the problem is way harder. So yeah. So, but I'm very curious. I'd love to. Could you send me the reference?
Sure. It's an old paper. We haven't looked at we redid the 3-band model, but didn't revisit the binding energy. But many years ago, we did compute binding energy for a sequence of cells and tried to extrapolate the thermodynamic limit for the Moire model. And it seems like it's very consistent. There's whole binding.
I see.
Couldn't find superconductivity.
And what is the recent? Again, I hope to this work.
So the recent thing focused on magnetic orders. I'll send you both. How's that?
Okay, please. Yeah, sounds great. Yes, yes.
It's just the magnetic order, the spin, basically spin density waves, spirals or charge orders are very similar to what we see in the one band model, this paper you mentioned. So we suspect that there's probably in the parameter regime we're looking at in the three band model, there isn't pairing either, a long range pairing at least, but we're not sure there. So there's this cross of, there's missing pieces numerically to say things more rigorously, but it's suggestive of possibly having hole binding but not superconducting order.
Yeah, I think in the case of when you have antiferromagnetic background, I think that problem is much more challenging. So that I think there could be that these could be two separate statements. The hole binding does not necessarily imply superconductivity. But in the case that I've talked about here, I think that it's much simpler system, so that should work. Yeah.
Thank you.
Hi, Liang. This is Zhiyuan from Columbia University. So I'm a little confused by this correlated copying. I guess it's represented by the lambda term, right?
Yes.
So to confirm, so lambda is positive, but
yes.
it has the attractive F-well channel.
Yes.
If you look at its momentum structure.
Right.
And then you have shown some analytical results for the TC and binding energy.
Yes.
From a continuous model.
Right.
Is that because the density of state in two dimensions is constant, so that you can get analytical results?
Oh, it's just because in the continuum theory, I can then quote results from Shi Wei. There's literature. Right.
So this ratio from between TC and the binding energy is like 4.7 something.
So that result actually I think is first obtained by I think that has a long history by Gorkov, I think. Gorkov, that there's some analytical work, yes, in the old days. And then there are also Monte Carlo results from Shi Wei. And my understanding, Shi Wei, please comment. Yeah, my understanding is that they agree quite well.
Yeah, that's a beautifully simpler case. Yes, those numbers are quite robust.
Yeah, it's actually very interesting. This, there are many experts in the audience. In that Gorkov paper is actually not just mean field. Gorkov actually, summed up more diagrams. That's as far as I can tell. I'm not a diagrammatic person, but they summed up high order contributions, and so that's why the expression is actually more than just the BCS value, more than a mean field, Yeah.
Oh, okay.
Yeah, I should put a reference there. This talk is prepared last minute.
So the only difference from the usual electrophonon-induced superconductivity is the cutoff energy changing from.
Exactly.
I see.
Yeah, and I think that is actually important also in the Moire materials. In the Moire materials, the bandwidth is so small, right? And I personally, if people want, I can talk about later, maybe after the questions. I have one slide comment on the Moire materials. So I do think that in Moire materials, the attraction already is present at level of 2 electrons, 2 dope electrons. I strongly believe that. Okay. Yeah. Just like in here, of course, the band structure is much more complicated. But the real question is, if you just add 2 dope electrons, right? You dope this, n equal 2 or n equal -2, right? You dope those insulating states. The question is, do you get a pairing for 2 dope electrons or not? Right? I believe that in order to explain the phenomenology, right, you have to get a pairing to get a bound state already for 2 dope electrons.
Okay.
And if that's the case, it means that the pairing interaction does not come from within the band. It comes from interband physics.
Okay.
Yeah, just like what I talked about here. And then it also follows that if that's the case, then delta over TC would be much larger than the BCS value, than the traditional BCS value. Yeah. Because the cutoff is different. Yes, cutoff.
Thanks. I have a second question, but regarding competing orders in this model. Yeah. So looks like for a small enough gap and high enough nearest neighbor interaction, there is an excitonic order.
There's an excitonic order.
Excitonic insulating state. Like you create a lot of excitons spontaneously.
But
I'm not sure about this. It just looks like if you look at the nearest neighbor interaction, it's an attractive interaction between electron and holes.
But at the fitting of n equal 1, right? The ground state is just it's still the boring insulator, right? At n equal 1, think of this way, right? At n equal 1, if you set the hopping t to be 0, right? You can have arbitrary large v and you can have arbitrary small delta, right? The ground state, as long as delta is non-zero, right? The ground state is still the simple charge order, it's a simple state, which is all the electrons are only a sublattice. Right. So as long as tunneling T is sufficiently small, then it's guaranteed that the ground state is a simple one at the fitting of n equal 1. So I think you're right that maybe as you increase hopping, then maybe something else.
Okay. Yeah. So I'm not sure about this. So maybe there's the Hartree stuff which can completely destroy this excitonic order. But okay, I'm just checking if you.
I mean, usually people think about excitonic insulator. There's always a question: is there a symmetry breaking involved? Right? If there's no symmetry breaking, the excitonic insulator seems to me no difference from band insulator or ionic insulator. Yeah.
Okay.
So unless there's a new broken symmetry, then excitonic insulator has become a meaning. I mean, to me, that's maybe different people have different.
Yeah, I'm talking about a broken symmetry state. Yes.
Right. So in this model, I think that at least when T is small, I don't think there's a broken symmetry state. There's just atomic limit.
I see. Yeah. Makes sense. Thanks.
I have one very basic questions. Will the picture of the correlated hopping and the bound forming be different if you study the system on different kind of lattice, or as long as the lattice is bipides, it's okay?
Yeah, I think certainly. I mean, the details will be different, right? Depending on different lattices.
Yeah.
But I think that this general picture is still true. There's basically. Think of that as like extone, right? Extone, interband extones will mediate some attractive interaction. I think that is probably very generic. Yeah. Yeah. So then what we can do here that has not been done before is this controlled way, the strong coupling expansion in the kinetic energy to handle this problem. Yeah.
And I also heard from the March meeting that the Pauli has a new recent experiment on trileography to find the BCS superconductor and the violation of Pauli limit.
Right.
So do you have any comment? I think your work is very close to that.
Yeah, actually, I have a mixed thoughts. Yeah, so I don't know the whether. So one possibility, of course, is triplet, right? I mean, the other possibility, I told Pablo this. This is an excellent question. Is that if you think about the delta over TC ratio that I have here, it's much bigger than a BCS value. So when he talk about Pauli violation, he's inferring, he's relying on this delta over TC is the BCS value. Yeah, so it's 1.75. Yeah. While so here, for example, we are 3 times larger than the BCS value. So then you actually may explain experiments already. So that's the one possibility here. Yeah. So I think one need really a direct measurement of the gap delta, not based on TC, and invoking the BCS expression, but one should just directly measure the tunneling gap. Yeah. Right. So, but that's it. Yeah. So it's an open question. It's an open question. It's an interesting, very interesting question. Yeah.
Is there any more questions?
So I have one. Will this mechanism always lead to unconventional pairing? So
yeah, excellent question. So I think generally, my general feeling is yes, because I start with repulsive interaction, right? Repulsive interaction. So So in the case of spin-full version, for example, right? You know, I have always a large on-site repulsion U, right? Because that is always there. You know, the interband process is kind of small compared to the on-site U. Mm-hmm. The on-site U generally doesn't favor S-wave pairing, but maybe there are loopholes. Yeah, but it's an excellent question. Yeah, in other words, I'll be very happy if I can find an S-wave pairing in this mechanism. I'll be done soon. Yeah. No. Okay. All right. So let me move to a different room. Sorry, everybody.
I actually, we have our grad student open house. I need to take off. So Liang, thanks a lot for the seminar, but other people can continue chatting if there's any other questions.
Okay. Thank you, Jen. Thank you, Jen, so much. Yeah.